Welcome to the second lecture on linear programming problem under this course on computational mathematics with Sage Math. In the last lecture, we saw how to formulate a linear programming problem and how to convert any linear programming problem into a standard form. Now, in this lecture, we are going to look at how to solve a linear programming problem in two variables using graphical method. So let us start with a problem. So the problem is to minimize x1 plus 3x2 subjected to these four constraints. The first constraint is minus x1 minus x2 less than equal to 9 by 5 minus 9 by 5, 2x1 minus x2 less than equal to 2, minus x1 plus 2x2 less than equal to 3, and 2x1 plus x2 less than equal to 6. Now first thing let us do, we will plot these constraints in the plane. Okay. Each constraint actually divides the plane into two equal halves. Right. So let us look at what is the region which is represented by all these constraints, and that is what is called feasible region, which we denoted by omega. So this is a Sage code in order to plot this region using region plot, and we are also plotting the each of this constraint, the line represented by the equality along with the borders. So let us execute this, and when we execute this, let us see what do we get. This is taking little time. Yeah, so this is the feasible region. Okay, so we want to solve this problem. So the solution of this problem is going to be points in this region. Actually, it turns out that the solution always lies at the corner point. So in this case, this feasible region has 4 corner points, 1, 2, 3, 4. So solution will lie on one of these corner point. Now each of this objective function, let us look at this objective function x1 plus 3x2. Now for various values of x1 plus 3x2, it will represent a line. So if you look at the contours of this objective function, that will be a family of line. So let us plot along with this region a family of objective function. So when we plot this is what we get. Okay, so you can see here this is the value of the objective function at 0.5, this is at 1, this is at 1.5, this is at 2, and so on. So as we go from 0 towards positive first quadrant, this what happens is the value of the objective function keeps on increasing. The problem is of maximization type, problem is of minimization type. This is to be minimize this function. So in case we look at this problem, the minimum value is going to occur somewhere here. That is the point at which the minimum is going to occur. In case this problem is of maximization type, the maximum is going to occur when the objective function value is somewhere here, which is close to 9. So that is the maximum value. So geometrically you can interpret this. If you just look at this, if you look at this constraint, if you move from let us say from origin away from the origin, then the point at which it just enters this feasible region, that the value will be the minimum value, and the one at which it just leaves this feasible region, that will give you maximum value. But there are various possibilities that we will see later. Okay, so that is how you can geometrically interpret. So first thing is to find out this feasible region, find out these corner points, and one way is to find all these corner points, and at these corner points you just compare the value of the objective function. If it is a minimization type, choose one at which the value is maximum. If it is a minimization type, choose the point at which the value of the objective function is minimum. That is how we can solve linear programming problem graphically whenever you have only two design variables. Now let us look at what are the corner points in this case? You can solve all these pair of equations. For example, this equation, this will give me this point. If I look at this equation and solve, this will give me this point. So in this case, we have just written a small code in order to solve two equations and find the solution, right? So there are 4 solutions in this case. One is 7 by 5, 2 by 5, and the value of the objective function at this point is 13 by 5, 1 by 5, 8 by 5, value of the objective function at this point is 5, 9 by 5, 12 by 5, value of the objective function at this point is 9, and 7 by 3, 4 by 3, the value of the objective function in this case is 19 by 3. So in this case, the minimum will occur at this point, which is 1 by 5, x1 is equal to 1 by 5, x2 is equal to 8 by 5, and the maximum is 9, which occurs at 9 by 5 and 12 by 5. That is what you can look at from this table. The minimum will be somewhere here and the maximum will be somewhere here. So that is the minimizer. This point is minimizer of this and this point is maximizer of this. Now let us look at how we can solve this using inbuilt Sage math function interactive LP problem. Interactive LP problem. Okay, so how do we do? So we will write these constraints. Whatever you have the constraint here, this we will write it as a list of rows in A. So this is first row, first constraint, the coefficient is -1, second constraint, the coefficient is -2, -1, third constraint, the coefficients are -1, 2, and fourth constraint, the coefficients are 2 and 1. The right hand side, which is B, that is represented as a list, as a tuple, so 9 by 5, 2, 3 and 6, and they are the coefficient of the objective function. This is C1, C2, so C1 is 1, C2 is 3, and so this is how we define this problem. Let me store this in capital P. This is called interactive LP problem. Then you write the coefficient matrix A, the right hand side B, and the coefficient of the objective function C, and the variable in this case are x1, x2, and the variable types are all non-negative. X1 and x2 are non-negative, and the problem type is maximization. This is a maximization type of problem. Here all the constraints are less than equal to type, so we don't need to give any condition. If they are mixed, you need to mention those type. In case it is a minimization type, here you write minimize. Now let us first ask it to show what is the problem. So you can see here this problem which is created using this by giving this matrix A, B, C in this interactive LP problem. It is exactly same as what we have started with. This is a maximization type, and here this was minimization type. So maybe I can also write here minimize or maximize. Okay, so this is the problem. Now once you have formulated this problem, then that is same as saying once you have created what is A, B, C and this problem P, then you can solve this. How do we solve this? So you can also plot actually feasible set, that is omega. So there is an inbuilt function called P dot feasible underscore set, and I have just said give me only figure size equal to 4. So if I run this, it will give me this feasible set along with these corner points. Unfortunately, I don't see this Sage reporting what are these corner points, but we have already found out. Okay. Next, you can also plot this P. So if you say P dot plot, then it will give you the feasible set, which is this F here. So you can see here there are 4 these constraints. One is x1 greater than equal to 0, which is this, x2 greater than equal to 0, represented by this pink region. Then you have this red line, which is x1 minus x2 less than equal to -9 by 5. So that is towards this side, and this is the corner point at which the maximum occurs, right? So that is the arrow, and this is the point at which the objective function has maximum value. So this is the feasible region, namely given by this, this. This is the feasible region, and this arrow represents the point at which the maximum occurs. In this case, maximum occurs. You can also find out P dot optimal solution. This will give you the point at which the optimal solution occurs, that is 9 by 5, 12 by 5. That is x1 is equal to 9 by 5 and x2 is equal to 12 by 5. That is where this problem has maximum value. And you can find out the value of this objective function. This is equal to 9. That is what we saw when we did this, when we solved these two equations, two lines, and found the point of intersection, that is those corner points, and the maximum was at 9, and that occurs as 9 by 5 and 12 by 5. So that is how you can solve linear programming problems in two variables graphically. What are the steps involved? First is look at the set of corner points, that is same as saying obtain this intersection of two of this this line represented by this represented by these constraints. Okay, so once you have obtained all these corner points, then evaluate the value of the objective function at all these corner points, and in case the problem is of maximization type, take the point at which the maximum occurs, and if the problem is of minimization type, choose the point at which the problem the objective function value is minimum. That is how one solves graphically. Okay. So of course in this case we have written this as a maximization problem. In case it is a minimization type, so if I convert this into min, then of course the feasible region will not change, but the minimum will occur now at different point, and that is this corner point, right? So that is and let us find out what is the minimum. This is at 19 by 15, 8 by 15, and the minimum value is going to be 43 by 15, and that is what I think there is some problem here. It's possible that we have written some constraint which is not as per this. Anyway, we will just look at this. Okay, fine. So let us look at maybe one more problem. This problem is maximize 3x1 plus 4x2 subjected to these three constraints: 3x1 plus 8x2 less than equal to 12, x1 plus x2 less than equal to 2, 2x1 less than equal to 3, x1, x2 non-negative. So again, if you define this problem, so we have to define A, which is the first constraint is 8 and coefficients are 8 and 3, second constraint coefficients are 1 and 1, third constraint coefficients are 2, 0, the right hand side is 12, 2 and 3, and the objective function, the coefficients are 3, 4. So let us define this. P is equal to interactive linear problem, LP problem, A, B, C. The variables are x1, x2. The variable types are all greater than equal to, that is x1, x2 greater than equal to. In this case, all by default, this interactive linear program will consider all inequality as less than equal to type. In case you have mixed, you have to mention it separately. That we will look at it later. Right. So this is the problem. It shows actually in LaTeX output format. Now let us plot the feasible set. This is the feasible set. The 1, 2, 3, 4, 5. There are 5 corner points. At each of these corner points, you can evaluate the function value and then choose one which gives you the maximum value of this objective function. So let us do it using inbuilt function. So if I plot this region, it says that the solution occurs at this particular point. So the objective function region here is this one, then this, then this, then this, then this. That's the omega, right? And in case we try to find out what is the optimal solution, it occurs at 4 by 5, 6 by 5, and the optimal value is 36 by 5. So that is how you can solve this this problem. Okay. Next, let us look at another problem. Problem 3. This is maximize z is equal to 2x plus 5 by subjected to these two constraints. So in this case, one is greater than equal to, other one is less than equal to. Again, x and y are non-negative. So instead of x1, x2, here we have considered x and y. So now if you try to define this problem, again exactly in a similar way, but now the constraint types we need to mention as a list of inequalities here. So first constraint was greater than equal to, the second constraint is less than equal to. Here though I have written variable type, first is greater than equal to, second is greater than equal to, but since both are greater than equal to, you need not mention. By default it will take non-negative variable types. Okay, so let us ask it to show this problem. So this is exactly what we have formulated. Now let us try to plot this feasible set. Now in this case, look at the feasible set. There is no intersection between these two inequalities. So therefore the feasible set is empty set. So that means you don't have any point inside this omega. Therefore this problem is called infeasible. Okay. So in case we can ask whether this P is feasible, is underscore feasible, it says that it is false. That means it is not feasible. So you cannot find any solution to this problem. Okay. Similarly, let us look at this problem. Maximize z is equal to 2x plus 5y subjected to these two constraints. And in case we try to formulate this problem and try to plot the feasible set, in this case, what you see, the feasible set is this one from here to here, then like this, and so on. So therefore, and this is actually infinite set. This is unbounded. Feasible set is unbounded. So this problem is what is called unbounded. It has feasible solution, but then the problem is unbounded. There won't be point at which the function value has maximum. Okay. So now let us check whether we can check whether this P is bounded. It says false. The problem is unbounded. Such problems are called unbounded problem. Similarly, if you try to find optimal solution, it will not give you anything because there is no optimal solution for this. Let us also look at one more problem. This problem, that is maximize x1 plus x2 subjected to these four constraints. And if we try to formulate this using an interactive linear program, this is what you get. This is exactly same as what you have. And then if you try to plot this feasible set, in this case, this is the feasible set. This is the feasible set. Again, it has 1, 2, 3, 4, 5, 6 corner points. So you can find out all these corner points and then you check value of the objective function. Now in this case, if you look at again in this case, if you look at this region and the contours of this objective function, what do you see? This contours, when we go away from the origin, the value of the objective function here is 0.25, here is 0.5, 0.75 and so on, and at this point this one has value 2, which is the maximum value in this case. You can see that is where it touches this this feasible region, that is where it leaves the feasible region. But then all the points between this point and this point will be a solution. At all these points the value of the objective function is 2, which is the maximum value in this case. Therefore this problem will have infinitely many solutions. Okay, why this is happening? You can look at the problem here. Here the value of the objective function is x1 plus x2, and one of the constraint is also parallel to x1 plus parallel to this x1 plus x2 is equal to c, right? So x1 plus x2 is equal to 12 is going to be parallel to one of these contours of this objective function. So in this case you have alternate solution or infinitely many solutions. In this case you have not just alternate solution, but you have infinitely many solutions. So we can take any point, for example this corner point will be a solution, any point on this line will also be a solution, right? So if you look at try to plot this p dot plot, and then of course it says that the minimum occurs here, but this line of this objective function line coincides with one of the constraint boundary, Therefore, any point on this is going to be solution, right? If you try to find what is the optimal value in this case, it says it is at 2, and you can also find out what is the point at which optimal value occurs. So let me just say P dot optimal solution, and then it will give me the point. So 3 by 2 and half is this is 3 by 2, x equal to 3 by 2, y is equal to half. That is the point at which the solution occurs. Okay, so let me leave you a couple of exercises, simple exercises. So solve these two problems using graphical method. So all you need to do is find out all these corner points, and at these corner points find the point at which the value of the objective function is minimum in case of minimization, value of the objective function is maximum in case of maximization. Of course, this problem, in this case we are asking for both maximization of this and minimization of this. Okay, so let me stop. Next time we will look at some basic definitions which we will keep using, plus some results without proof we will look at, so that based on those results we will develop what is called simplex methods or theory of simplex method. Thank you very much.